Okay, so in review, we did this first, right? Electronic spectroscopy, and then we took that excursus and talked about molecular orbital theory, and we generated that diagram on the left. Now let's go back and look at electronic spectroscopy again. Not the whole lecture, but just again, with that molecular orbital diagram, the atoms come together. And when they come together, you get the molecular orbitals. Because what touches when atoms come together? The electrons, yeah, the electron cloud, the valence orbitals, the atomic orbitals and the valence shell, the outermost shell, start to interact with each other. And as they get kind of closer together, you start to see bonding and anti-bonding arrangement, and those electrons start to move into bonding arrangements. What does that set up for the two atoms? Attraction. So they get pulled together, and so that's what's happening here. The two atoms are coming along. They've got their atomic orbitals. They're happy as atoms, but then they start to interact with each other, and those bonding orbitals start to like the electrons start to form bonding arrangements. And they're 1,000th of the mass of the nuclei. So as the nuclei are moving close together, the electrons have all the time in the world to adjust. And so they form these bonding arrangements and snap together. If they get too close, the nuclei start to see each other, and then you start to get repulsion. And so they snap together, they give off this energy in terms of infrared photons perhaps, or whatever, they collide or something like that. But anyway, they get stuck together, and they end up in that minimum, oscillating around that minimum. So that's how a diatomic is made. Atoms come together. They don't have so much energy that they collide and go back. Sometimes that happens. In fact, let's look at that. If they had enough kinetic energy, they would form this bonding arrangement. So there's velocity, they're colliding. They form this bonding arrangement, but they have enough energy that they end up here on that potential energy surface and stop. So they've gotten so close together that the repulsion of the nuclei is enough to drive them apart. And so if you were to turn around right there, if you had that much energy, you turn around, they fly back through that minimum and then back out as two separate atoms. So that's kind of what's happening during a collision. If for some reason they come together fairly slowly, then they can react. So they have enough kinetic energy to collide, but not enough to repel. And so it's an inelastic collision. They get stuck to each other, and the energy that's excess vibrational energy is emitted in the infrared, or maybe they collide with some other molecule and give some of that excess energy away. But they do that non-radiative relaxation, and they end up in the ground state. So that's what's happening during a collision, and that MO diagram starts out with just the atomic orbitals, and then they come together and they split into the molecular orbitals, and then they may collide, and then they go back out to the atoms, or they come in and they form the molecular orbitals and they get stuck. And as they oscillate, the orbitals get closer together and further apart. So they're doing this the whole time when they're stuck together. As those molecular orbitals are spreading apart when they get close together and squeezing, getting closer together as the atoms get far apart. So they're doing this. So that diagram on the left is kind of a dynamic diagram. As the nuclei move, the electrons are able to interact immediately with each other. And so in a ground state atom, it's oscillating like this. There's a little bit of a response in the electric potential surface with the vibration, but mostly they're down here in that bottom electrical potential. And so now let's go to the board and we'll make a spectrum from this thing on the right. So we'll start with the potential energy surface diagram, and then we'll make a spectrum, an absorption and an emission spectrum. Okay. So this is going to require a new sheet of paper in your notes. Let's do this. Let me come over here and find my boundaries. Okay. So So draw your ground electronic state. So that's the X, which indicates the ground state. There may be some others that are the same, but then we'll come up here, like in the iodine, we went up to the B electronic state, and it was up here somewhere. Go ahead and draw your ground vibrational level pretty close to the bottom, and label that 0 double prime. Okay, so you put a little 0 there and a double prime to show the double prime means it's in the ground electronic state. And then up here we'll put the ground vibrational state as 0 prime. So these are our two potential energy surfaces, and then across this x-axis, that's the internuclear distance. So R in, we'll say in angstroms. R in angstroms. I realize you can't see that over on the far right. So this is just, I put the x-axis here and put R in angstroms. Okay? And then this vertical axis is energy. Already, if we were to look this up for a molecule, we could say some things about our molecule. Okay? What's some of the information we could pull out of a potential energy surface diagram like this? So, help me out. What could I learn about my molecule from this plot? Go ahead. I heard somebody whisper. Oh, you're wrong? Well, say something. Get the ball rolling.
Can't you know, like, the electronic distribution based on where the center of the bottom peak is and carry it up and I'm like, look how far over the other bottom peak is?
Let's talk about how far over. What are the minima here? What's the x-axis? Internuclear distance. So the minima are the bond lengths. Okay, so the minimum of this potential is the ground state bond length. When I say ground state, I mean ground electronic state. And the ground vibrational state. Okay, you have two different things going on here. You have electrical excitation and ground electrical state, and you have vibrational levels as well. So you have two different quantum numbers, two different things going on. But that's the bond length of the ground electronic state and the ground vibrational state. And this is the bond length of the excited electronic state. And so another thing you could learn too, why is the bond length longer for the excited state? I don't know, since I don't know what molecule this is, but we'll say it's iodine. We've taken a bonding electron and put it in an antibonding electron. That's the most common situation when you have a lengthening of the bond. You've taken an electron out of an orbital, molecular orbital that supports the bond, and put it into an orbital that's not supportive of the bond, or an antibonding orbital. And so you've got the electron cloud doesn't support the bonding as strongly as this one. So each one of these electrical potential energy surfaces, electronic potential energy surfaces, corresponds to a different molecular orbital diagram. Okay. So that's a lot of things that we can learn from this potential energy surface. There's one other thing here. What about this distance here? This is the energy axis. What can we learn about the energy between these 2 points? Dissociation energy. Yeah, so this also shows that the excited state is a weaker bond because it takes less energy to break it apart. Okay, so going from this, the bound state, this is the ground vibrational state and the excited electronic potential energy surface. I can break that bond by giving it this much energy. I have to give the ground state, electronic state, this much energy to break the bond. So does everybody kind of feel more comfortable with the potential energy surfaces as they're plotted with bond length? If you're uncomfortable, tell me what you need clarification on, or if you have anything that you want to ask. Yes?
So if you said to estimate, would you have to estimate the bond length? Is that what
Yeah, so if we had tick marks on here and numbers, then you could tell me what the bond length was for the ground state. You could tell me what the bond length was for the excited state. You could say the excited state has a weaker bond. It's both easier to dissociate and it's longer. Okay, so just given the potential energy surface, you can answer a lot of questions about it. if you just look at the axes, again, you got energy plotted versus bond length or internuclear distance. Okay, these little points here are actually the bond lengths, but the whole x-axis is the distance between the two nuclei. Okay, and so you could say the minimum here and the minimum there. This is the excited electronic state, the ground electronic state, vibrational levels here and here. So now this is the potential energy surface diagram. Over here, let's plot the spectrum. I'm going to kind of nestle it up so I don't have a lot of room. But so we'll have, I'm just going to put signal on the y-axis. Let me do this in a different color. And we'll do a visible spectrum. So 400 to 700 nanometers. And if we're way over here to the right so this is the vibrational energy level. It has it's got a wave function that looks like this. Okay. It's a Gaussian wave function in the ground vibrational state. Notice there's some probability that I'm pretty far stretched, right? So over here the molecule is stretched pretty far apart. Over here it's compressed. If you were to take a snapshot of the molecules, most of them would be in the middle. A few would be compressed, a few would be stretched. Light comes in, sort of takes a snapshot of the molecule, matches the 0 to 0 transition, and you can get absorption. Okay, so if we draw this line vertically, and I realize if your levels didn't quite line up to where the 0 and 0 could overlap, go ahead and pretend that they could. You could tilt your arrow a little bit, but most of these arrows by definition are vertical arrows. It's straight up because the nuclei don't have time to move with the speed of light. Light comes in, pow, you get absorption. So that's the 0 to 0 transition. And so we're going to say that's around 500. Okay. So that's the 0 double prime to 0 prime absorption. And it's a pretty small peak. Can anybody tell me why or how I know it's a small peak? This is the wave function in the excited vibrational state. And this is the wave function in the ground vibrational state. And how much do they overlap? Very little. I take this function as a function of r and multiply it by this function as a function of r. And that tiny little overlap, where they overlap, is called the Frank-Condon factor. And that was one of your vocabulary words. You had the Frank-Condon principle and the Frank-Condon factor. And the factor is actually the integral of the overlap of these two wave functions. The principle says that the intensities of these peaks will be related to the overlap of the wave functions. And then the actual factor is the overlap of the wave functions. Do you understand the difference between the principle and the factor? The factor is actually the result, the overlap of those wave functions. The principle is that you could use that factor to calculate the intensities. Okay, so this is a tiny peak because of the Frank-Condon principle. For simplicity's sake, let's just do three transitions, in the absorption. Okay, so I'm going to draw two more levels up here. I'm going to call that 1' and 2'. Okay. Good one. Okay, and so then we have this wave function. Isn't that neat? It kind of looks just like our particle in a box. Okay. So that's why we did that particle in a box thing. These are one-dimensional wave functions in vibration. Notice the turning point is a little bit further to the left. And so the overlap with my ground state wave function is going to be higher, isn't it? Okay. And so then over here, I'll have this one, which is a little bigger, and this one, which is a little bigger. That's the 0 double prime to 1 prime, and the 0 double prime to 2 prime. So we're going to different vibrational states in the upper electronic potential energy surface. So do you see how we went from the MO to potential energy surface diagrams, and then from there to the spectrum, and we're doing absorption. Absorption, all the arrows are going up. We're at the ground vibrational state, in the ground electronic state, going to multiple vibrational states in the excited electronic state. Okay. Now, you might imagine that if we keep going up, eventually these vibrational wave functions would be on the other side of our ground state wave function, and the intensities would start to go down, and they do. So I'm going to go ahead and draw the others as they go down. So we would have a maximum, and that would be the maximum of that Frank-Condon factor. It's the ground vibrational state. You see the way it looks, the shape, this Gaussian shape, looks just like this. Okay, it's not an exact match, but it's what's giving us this intensity pattern here. That's the Frank-Condon principle, that ground vibrational state will give us the intensity pattern in the absorption spectrum. Okay. You had a question.
So the wavelength is decreasing for these as you're increasing like the energy level?
Yes, yeah. So the energy of these arrow differences. So again, so these are the energy levels. Let me go ahead and write that down in green. Levels. And then over here, these are lines. So this has been a theme through the whole course, that the energy level diagram we really can't see. We do see the spectral lines. And the spectral lines are always differences in the energy levels. So we have 0 double prime to 0 prime. That's a difference, and the length of that arrow converted to wavelength is right here. So the spectral lines are differences in energy levels. And we did those transition equations. E of j plus 1 minus E of j. E of n plus 1 minus E of n. And the selection rules gave us those delta j's or delta n's. We have open selection rules in electronic spectroscopy. So we can go from 0 to 1, 0 to 2, 0 to 3, 0 to 4. There's no restriction on delta V. There's no restriction on the electronic jumps, except you can't flip a spin while you do the absorption. Is that good?
Yeah.
So as that arrow's longer, and so it's the shorter wavelength of the three. Yeah. And so all of the absorptions, the longest wavelength one, and this is a principle that you can say, the longest wavelength absorption is going to be the 0 to 0. Longest wavelength means shortest arrow. Those are closer together than any of these others.
And then the peak increases because it's moving along.
This ground state wave function is mapped upon those levels. Yeah. And so you can tell from the maximum peak here. So I count this up. Let's say I didn't have these labels here. The very first one, the longest wavelength one, is the 0 to 0. So then I can count to the left, 0 to 0, 0 to 1, 0 to 2, and then they start going down. So that tells me the 0 to 2, that this point right here is directly above the maximum in the ground state wave function. This point right here on the 0 to 2 level, that's the turning point, is directly above the vibrational wave function midpoint, the maximum of that vibrational wave function in the ground state.
So the next one is still going to be the 0 to 3 prime?
Yes.
Goes down?
Yes, and 0 to 4 prime, 0 to 5 prime. Yeah. And so in order to simplify things in the iodine lab, we had this little deal like this. We had 0 double prime here, and we had 0, and then a tick mark, and a tick mark, a tick mark. And then, so this kind of goes along. And then this tick mark was labeled 5, right? So we went from 0, 1, 2. So these are the primes. So this was 0 double prime to 0 prime, 0 double prime to 1 prime, 0 to 2, 0 to 3, 0 to 4, 0 to 5. So this is the 4 one. So do you see how to read that? It was just an easier way. You'll see this kind of diagram in the literature when they assign a spectrum. And this gets really busy with all these numbers and arrows and everything. And so they'll do it this way. And that was exactly the way it was done in your iodine lab. So I'm just reinforcing the material you learned in the iodine lab, because that is a classic PChem lab, is to assign a spectrum of iodine. I mean, across the world, PChem students do that. And so you got to know how the assignment is written out. Okay. And that is definitely on the test. So knowing how to read this little deal with the numbers, the quantum numbers, and the peak assignments, that is something you need to know. Okay. That's part of getting through PChem. You can't get your bumper sticker without that. Okay. So now let's do emission. So this is absorption. We can learn something about the ground state wave function by the maximum of this peak. But we learned the differences. What do we learn from the differences between these wave functions? Right, or between these peaks, these spectral lines. So if I look at the difference between these two spectral lines, what am I actually measuring? I'm measuring the difference in vibrational separation in the excited state. So listen carefully. The absorption spectrum tells me about the vibrational spacing in the excited electronic state. It's a long phrase. Listen carefully. The absorption spectrum tells me about the vibrational spacing in the excited electronic state. It tells me nothing about the ground electronic state. Look here. The ground electronic state is 0 double prime for all of these peaks. The only information I get by looking at the differences in these peaks is the difference between 1 prime and 0 prime, or 2 prime and 1 prime. So I'm learning all about the electronic excited state when I'm doing absorption. And that's what you had for the iodine lab. Now the iodine molecule is so big that the masses, that you had some thermal excitation in the ground state. So you did have a 1 double prime series and a 2 double prime series, and that made that lab really hard. Okay, it would have been much easier if we just had 0 double prime and learned all about the excited electronic state. But we had you had other information in there. You had another series in the absorption from the 1 and another series in the absorption from the 2, and they all overlapped, and it was a pain to assign. But you did it. Okay, got through it. But now let's look at emission. So this main peak gets up here into the 2 prime level, and then it works its way down, spitting out tiny little infrared photons, which we don't see in the visible spectrum, so we call those non-radiative. Okay, so there's another vocabulary. Non-radiative relaxation is it just getting back down into the excited electronic state, but the ground vibrational state. So they collect right here where that orange wave function is, and then it starts to emit. Now, let's draw these arrows in zero. So go ahead and put a 1 double prime and a 2 double prime on here. So 1 double prime and a 2 double prime. And we're going to draw an orange arrow, again, 0 to 0. So this 0 to 0 can go up and it can go down. Okay. But one thing I want you to notice, if I go from 0 in the upper state to 1 in the lower state, notice the arrow is shorter, not longer. In emission, when I'm going from 0 here to things other than 0 here, I have shorter arrows. So I'm going down. And so all these vibrational levels get closer to where I'm at. And so all these arrows are shorter, which means all these arrows are redshifted. They're longer wavelength. And so if I go from 0 to 1, then that peak's going to be here. And if I go 0 to 2, that peak's going to be here. And it's going to be a little bit higher intensity because it's closer to the middle of this wave function up here. And because it's closer to the middle of this wave function, the Frank-Condon factor is higher. And so the intensity in the spectrum is higher. So then this is the 0 prime to 1 double prime. And this one is the 0 prime to 2 double prime. And so this is what we would see on the absorption side and on the emission side. And so we could draw our little bar here, starting at 0 prime and going to 0 double prime, 1 double prime, 2, 3, 0, 1. Got 5 on the wrong number, so let's do this again. 0, 1, 2, 3, 4, 5. So again, the same kind of assignment, but now it's going this direction. All of these start at 0 prime, which is in the upper electronic state, and they go down to the vibrational levels in the lower electronic state of 0 double prime, 1 double prime, 2 double prime, 3, 4, 5, etc. You have the same kind of intensity pattern here from the Frank-Condon factors of the upper vibrational state overlapping with the lower vibrational states. And all of the emission peaks are to the long wavelength side. They're red-shifted from the excitation peaks. So the absorption peaks here excited the molecule, and then the emission peaks are the radiative relaxation, spitting out visible light as we drop down electronically. So this is absorption on the left, fluorescence on the right. We haven't had any spin flips. These are, it's iodine, so these are both singlets. This is a singlet ground state and a singlet excited state. So we've excited an electron, it's vibrationally, relaxed a little bit, but then we spit that electron back out. And so it's a singlet in both cases. Singlet governs the whole molecule, so you can have electrons in other orbitals, but still add up the total spin to be 0. And so, now in practicality, when you have this situation, you typically do these experiments separately. Like you'll do an absorption spectrum in a visible spectrometer, and so you'll only get the blue spectrum. But we have a fluorescence spectrometer that you'll get to use in instrumental. And when you get there, you'll put the detector at a particular wavelength, and you'll scan the absorption spectrum, and you'll get a spectrum like this. And then if you want this spectrum to be as tall as possible, so you have the most sensitive technique, you sit at the maximum here. And so you'll set the excitation wavelength, and you'll sit right there, and you'll just keep pumping molecules up to 2 prime. And they relax, and then you get the largest possible peak in the emission spectrum. And so that's how the fluorimeter works, is you pick an excitation wavelength, and it makes sense to pick the most efficient one, the tallest absorption peak. And so you'd set your excitation wavelength right here, And you would just be pumping them up to that level. And it's just efficient pumping. And then they relax down. And then you get efficient or very frequent fluorescence. And you would get a very sensitive spectrum here. What if you sat at one of these lower peaks? Then all of this fluorescence spectrum would just drop down a little bit. And if you eventually got off of the excitation peak, then you wouldn't have any signal from the fluorescence at all. What else could I say? If you were able to pump it efficiently enough, you might get a population inversion, okay? Which would be useful if you wanted to turn iodine into what? A laser, yeah. You make a gas laser, an iodine laser. You'd have flash lamps to pump all of the iodine molecules up here, and then you'd have a resonant cavity where these photons could go quickly back and forth through the iodine gas and build up a coherent emission spectrum. And you'd have several laser lines. You know, they would go to each one of these levels. And so you might put a monochromator in there, like a little prism or a grating, and filter out just one line. And so a photon might come out at one of these other levels, but it gets knocked off the mirror and doesn't go back through the cavity. But if you picked this one here, it goes through, hits the grating, hits the mirror, comes back through the grating, and goes back through the gas. And so you can just build this one line up and have a really bright laser signal coming out of that. But you could use this system to, again, efficient pump to the 2' level, non-radiative relaxation. And if you get a population inversion and you put it in a resonant cavity, then you could have a laser. That's, I think, a pretty good review of electronic spectroscopy. And it's related to MO theory because MO theory gives us these potentials. So with that, we've got 10 minutes for questions. Yes?
Did it matter to you exactly where we plotted the peaks on the spectrum?
No, like I don't really, I mean, I'm just building the picture mostly. It's not too accurate in terms of what wavelength, yeah. Because I don't even have any energy numbers. Now, if I did have an energy number, which I don't freak out, but if I did, and this was 20,000 wave numbers difference, then you could figure out what wavelength it was. You take 20,000 wave numbers and convert that to nanometers, okay? And the conversion is it's a 10 to the 7 nanometers per centimeter. If you just look at the metric system, and this is, wave numbers is inverse wavelength. So it's 10 to the 7 nanometers per centimeter divided by 20,000 wave numbers. So the per centimeter cancel and you end up with nanometers. So just follow your units. 90% of the PChem problems are units, well maybe 80%. And so if you just follow the units, you can do those things. But you've got to realize, and this I think caught some people on the last one with the spectrum simulation exercise. I don't think anybody tried that one. But anyway, you could take the energy difference, convert it to wavelength, and plot that because the lines are differences in energy levels. And so if nothing else, you know, it's at the end of the day, what are you going to remember from PChem? That lines, spectral lines, are differences in energy levels. And if you ever have a question about a spectrum, you need to get to the point where you can plot your two energy levels and understand something about the molecule before you can understand the spectrum. And so that's why you get out the cocktail napkin and the pen and you say, okay, I don't know about the spectrum, but what are the energy levels we're dealing with? Are these atomic energy levels? Are they vibrational energy levels? Is this rotation? What are my energy levels? And what does that tell me about the molecule? And if I can understand why the energy levels are what they are, then I can understand what the spectrum is telling me. Is it a homoluminal gap? You know, is it ionization? And we knocking an electron all the way off? So understanding what the levels are will help you understand the spectrum. Next question. It always looks so easy on reserve review day, you know. Y'all did a pretty good job on the vocabulary. I think I added a couple of words that were just like dramatically missing. Okay, but I finalized it, closed it for editing, so you can study that. Do your Quizlets. Okay. I think I should tell you that the multiple choice, y'all are doing so well. I want to squeeze you a little bit, so it's all just fill in the blank on this instead of 20 multiple choice. So you got to up your game a little bit. You got to know those words. So, yes.
Could you do a quick review of the Jablonski diagram?
Okay. Yes. So this is pretty complicated with all of these vibrational levels, and so all they did. For the Jablonski diagram, I'm just going to edit this a little bit here. I'm going to draw it right next to this. So the Jablonski diagram has an x-axis and a y-axis. The y-axis is energy. And the x-axis is not really discrete values. I mean, not really a continuous axis like distance. It's just singlet 0, singlet 1, triplet 1, and so on. And so then they take this ground state vibrational manifold and they'll plot it as just a vertical box with a bunch of lines. And so those lines are supposed to represent the vibrational energy levels, but they're not necessarily accurately plotted. I guess you could make an accurate Jablonski diagram, but you would set that ground state at 0 energy. So that would be your reference point, the ground electronic state. And then up here for S1, you would draw another one. And so then this would be the difference between those electronic states. So this would be, I would say, so the energy of S1, the ground state energy of S1, the ground vibrational state of S1. So this, and so we might write up here B and X, if we knew what those were. So this is X here, we're calling that S0 in the Jablonski diagram, singlet 0. And then this is the B state, that would be the next excited electronic state. Okay, then we might have a triplet one. We don't have this shown on here, but this might be T1. I don't know if it's 1 or 0. I have to go and look at the convention. It's 1, okay. And so this has a slightly lower energy because typically if I've got a singlet excitation and then I unpair those spins, the whole molecule drops in energy a little bit, so the triplet state is a little bit lower. So this is the Jablonski diagram. Notice the x-axis really isn't a coordinate. It's just categories of S0, S1, T1. And so we can show then this that's the 0 double prime to 0 prime transition. And then going the other direction with the arrowhead, that's 0 prime to 0 double prime emission. Singlet to singlet transition, what is that orange one called? Fluorescence, yeah. If I did a little switcheroo down here and went over to the T1 state, what's that called? Inter something. It could be, I can get that far, right? It could be internal conversion or inter-system crossing. I'm going from singlet to triplet. That's causing a spin flip, and so it's inter-system crossing. If I went the other way, that would be internal conversion. I know it's kind of ugly. I'm trying to make the most busy page ever. And then if we get down here to the lower of the triplet state and we go down, that's phosphorescence. So I went ahead and labeled these fluorescence because my Jablonski diagram was too busy. Okay. So singlet to singlet, or here's the thing that y'all messed up, or at least we're potentially messing up. Triplet to triplet is also fluorescence. So there's no spin flip. If there's no spin flip, it's fluorescence. If there is a spin flip, it's phosphorescence. Everybody catch that? Okay. Intersystem crossing changes triplet to singlet or singlet to triplet, vice versa. Internal conversion is singlet to singlet or triplet to triplet. Again, if you change manifolds, these are manifolds, if you change those without flipping a spin, that's internal conversion. If you flip a spin, it's intersystem crossing. And we could, in theory, get from S1 all the way down to the ground state by non-radiative relaxation if we have internal conversion. So if we get to this point and can jump over to that one, we can keep going down the vibrational manifold until we get to the ground state, and we won't ever see fluorescence. And so for molecules that don't fluoresce, that's what's going on. They're getting visible photons in, and then they're able to shake all that energy out vibrationally and not have to emit any visible light. Typically rigid molecules will not have as much vibrational flexibility because they're rigid, and so they'll fluoresce. So aromatic rings fluoresce like crazy because the vibrational manifold in that rigid ring is one of the things that causes it to fluoresce. Yes.
So that to happen with the D, little
Yeah.
squishy D has to
Yeah,
be
you'd have to have
under
some overlap between this and this. Yeah,
It has to be all the way down under, at least in this is.
like here. Yeah, that's right. It has to have some way to intersect this potential energy surface. Yeah, nice. Okay, we are out of time. But I think that really prepares you. If you can do the MO diagrams and you can understand the symmetries that we've been doing all semester, and then this spectral piece. Yes.
Or the CS.